Hello everyone, I'm James and welcome to episode 10 of the OpenGL tutorial series. Today we're finally doing normal mapping. I love normal mapping, it gives so much detail to our scene without adding additional geometry. So how does this work? Let's go ahead and begin.
This here is a flat surface, and because it is flat, the normals are all pointing straight up. If we had a rough surface, these would be its normals. In the last video I explained how the difference between the surface normal and the direction to the light from the surface affect the final lighting result. Now let us go back to the flat surface. What happens if we use the normals of the rough surface on the flat surface? Since the lighting calculation uses the surface normals, the surface would be lit as if it is a rough surface. This effect gives a lot of detail without adding additional geometry, which is why it's so useful. But how do we get all those bumpy detailed normals? This is where the normal map comes in. The normal map is an image like any other. However, the colors of the image represent the surface normal offset we want. The red channel represents how much we want to offset the normal on the x-axis. The green channel represents how much we want to offset the normal on the y-axis, and the blue channel represents how much we want to offset the normal on the z-axis. In this case, the z-axis represents the up direction of the surface normal.
You might be wondering why am I saying that the normal is the forward vector? Isn't the normal pointing upwards? Well, yes. If you look at it from a certain perspective. We're looking from the perspective of the surface, so it's as if we are the surface, so the normal is going out of us, forward. That's why it's the forward vector. Hopefully you understand.
As you can see, the entire image contains blue. This is because the normal should never be pointing downwards. This is all well and good, but what happens if we transform our mesh? If we move or scale the mesh, everything will be fine. But what if we rotate the mesh? I think it's pretty obvious that this isn't right. What we need is some rotation matrix that will be able to rotate our surface normals so that they will be in the proper orientation. We can easily construct a rotation matrix from the forward, up and right vector. How do we get these vectors? We already have the forward vector, which is the surface normal. We then need what is called the tangent. This is the right vector, which is perpendicular to the normal. Then we need what is called the bitangent. This is the up vector and it is also perpendicular to the normal. How do we get the tangent and bitangent? We need to do some calculations to get the tangent. However, once we get the tangent, we can easily get the bitangent by doing the cross product between the tangent and the surface normal. So let us start by adding tangents to our system. In the vertex class, we'll add one more field for the tangent, and I'll initialize it in the constructor. However, I'm going to default the tangent to 0. In the mesh constructor, we'll enable attribute tree. Setting the attribute pointer for the tangent is very similar to setting it for the normal. In fact, I'm going to copy and paste and change what needs to change. The first thing that needs to change is the attribute index, which is now 3. The only other thing we need to change is the offset. We now need the offset of the tangent field. In the vertex shader, we need to add another attribute for the tangent. Now instead of passing the normal as a varying variable, we'll pass what is called the TBN matrix. This is the rotation matrix we mentioned earlier, which is made up from the forward, up and right vectors. This rotation matrix is going to be a 3x3 matrix. We still need this calculation, so I'll store it in a new variable called n. We also need to transform the tangent. And we'll do this in the exact same way we did with the normal, except using the tangent. Next thing we need is the bitangent. As I already mentioned, we can get that by doing the cross product between the tangent and the normal. Finally, we can create the TBN matrix out of these three vectors. In the fragment shader, we'll take in the TBN matrix instead of the normal. Next, we'll take in another texture uniform for the normal map.
It was at this moment I realized that I accidentally left a multiplication by 2 when sampling the texture. Well, I'll remove that, so yeah. Sorry about that. In the future we'll add some either float or a vec2 to be able to tile the texture at a certain frequency. But yeah, let's continue.
In the main function, we'll sample the normal map. Each channel of the color is between 0 and 1. We need the normal's components to be between -1 and +1. We'll fix this by multiplying the color by 2 and subtract 1. We also only care about the XYZ components, so I'll swizzle the vector to get the XYZ components. Next we'll rotate the normal with the TBN matrix, and then we'll normalize it. Finally, we can use this new normal in the calclight function call. Back in the C++ source code, we're going to add a normal map texture to our material. Since we named the texture with the same name of the texture class, I'll rename the field to diffuse. We'll initialize the normal map in the constructor. In the update uniforms method, we'll bind the normal map, this time in slot 1. It's very important to also set the uNormal map uniform to 1.
I'm not going to explain how to calculate tangents because there are other tutorials that explain how it works much better than I can. So I added a bunch of things off screen. In the mesh loader, I added calculating tangents. And in the in the mesh source file, I added a calc tangents function, which I'm calling when I do create cube, which we're not using right now, and the load terrain, which we are using right now. There you go. In the scene, I'm loading two textures. I'm loading the bricks normal.png and the blank normal.png, which I've just created. The blank normal is just a light blue like this. That means there will be no normal map. There are two normal maps because one of them has the green facing upward, so you can see the cyan color is made from green and blue, and it's on the top side of the bricks, and in this image it's on the bottom side. Basically the green is inverted between these two. The reason for this is there are kind of two standards. Sometimes normal maps are in this format and sometimes they are in this format. Ideally you stick to one format and you can modify the code if you want. You can go in the shader and actually modify the code so that the X or the Z is inverted. In this case, the Y or the X is inverted. In this case I believe it's the Y. Yeah, it's the Y coordinate that is green, so you would flip that. So if I run now, we get, look at that, normal mapping. It might be not so obvious right now, but you can see that there are kind of crevices there for the bricks. What really doesn't look well is the way we are, what doesn't look right is the size of the texture. We want to tile this texture quite a lot, at least, to make it look a bit better, let's just say that. So I'm going to do this right now. I'm going in the material and I'm going to add a new property. It's going to be a vec2 for tiling. We can make it a float, but this is more flexible because we can tile in X and Y with different amounts. I'll do shader set uniform, and I'm going to add a uniform U tiling factor. In fact, yeah, I'll call it tiling factor and tiling factor. This is going to do a bit of a snowball effect. First of all, yeah, make sure you use tile factor. As you can see, we don't have a set uniform function that takes in a GLM vec2, so let's do that right now. I'll add in the shader header, I'll add a new method. It's going to take in a vec2. It's actually very easy, that's why I'm doing it like this right now. So I'll copy the vec3 and I'm going to make it though taking a vec2, and we don't take in this z component, and we call gl uniform 2f instead, and that's basically it. So now we have the tiling factor, and now the error is gone, and we'll add a parameter for that. So here we go, tiling factor, which I'll actually default to 1 as well, and I'll set tiling factor to tiling factor, which I misspelled, so it's tiling factor like that. Okay, now in the shader we're going to add this new uniform vec2 u tiling factor, and all we have to do is multiply this u tiling factor by the text chord, both when we're sampling from the normal map and even when we're sampling from the texture, from the texture. With that, if we run, we should get the exact same result because we haven't added any tiling. So if it's just like before, no, we get an error. Okay, so apparently I've made a mistake somewhere. U tiling factor, right, I made a silly mistake. It should be a vec2, not a vec3. Now if we run, there we go, we get this exact same result. Let's add some tiling. So in the scene, I'm going to set the color to 1, just white, we don't care about the color, and I'll set the tiling to, let's say, 20. So 20. And now if we run, there we go, look at that. It looks cooler, doesn't it? Yeah, and we have the bricks with normal mapping. You can see it's very apparent right here, for example. You can see the bricks are kind of beveled. Amazing, so we have normal mapping as well. There you go.
And that, my friends, is the end of this video. In the next video we're going to be making a skybox, so that we don't have a black background anymore. If you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell to be notified when the next video is coming out. With that, thanks for watching and goodbye.